Going over last night's assignment, which was to complete the first 5 problems. Number 1 dealt with a plane being 6 miles above the ground, approaching a radar station 10 miles away, diagonally in the air, and the distance between the plane and the radar station was decreasing at 400 kilometers per hour. And then it said, how fast is the plane flying horizontally? So it's asking for dAdt. The formula that we are given, or we're going to use, is a squared plus b squared equals s squared. And then from here, we're going to implicitly differentiate each of these with respect to time. So what's the derivative of a squared? 2a. And then we're taking it with respect to time. So since the variables do not agree, we've got to put dAdt plus 2b dB dt equals 2s ds dt. Going through and looking at this, we've got to have ds dt, we have that. We have to know s, we have that. dB dt we know. B we know. dA dt we do not know, that's what we're looking for. And we said in order, and then we need to know everything except for what we're asked to find. So we need to know a. We do not know a, but we can use this formula to find a. So we do a squared plus b squared is equal to s squared. And we can plug in 6 for b, 6 kilometers squared equals 10 kilometers squared. We get a squared plus 36 kilometers squared equals 100 kilometers squared. A squared is equal to 64 kilometers squared. And then you square root. What's the square root of 64? 8. And what's the square root of kilometers squared? What's the square root of kilometers squared? Just kilometers, which is what we need it to be. Okay, so now we have enough information to fill in this formula. So we just go through and we fill it in. 2 times 8 kilometers times, well, we don't know what dAdt is, so we're just going to leave it as dAdt. Plus 2 times b, which is 6 kilometers, times 0 kilometers per hour, equals 2 times s, which is 10 kilometers, times ds dt, which is negative 4 kilometers, or negative 400 kilometers per hour. Everything here becomes 0, so we're just going to mark it out. So what we have is we have 16 kilometers times dA dt is equal to 2 times 10 is 20, so we should have negative 8,000. And what's the units attached to that? Kilometers squared per hour. So we have kilometers times kilometers per hour. And then to solve for dA dt, what do we do with the 16 kilometers? Divide it over. dA dt, negative 8,000 divided by 16 is negative 500. Kilometers squared divided by kilometers makes just kilometers per hour. So our units match up with what we should get. We get negative 500. That makes sense too because it's flying towards the radar station. This side of the triangle is getting shorter. Therefore, we should have a negative speed, negative velocity. Okay. Going with the second one, we tried drawing the picture. I said let's put x here. That didn't work out because there's no proportion. We need bases to top, bases to height, bases to height. And we have to use variable expressions on what's going to change. So we have the shadow, or this distance is changing and the shadow is changing. We have to use x and y for that component. Implicitly differentiating, we have to use the product rule. Product rule says you take the derivative of the first times the second plus the first times the derivative of the second. And then equals the derivative of 40. The derivative of x is what? 1. So we just get 1y plus x times the derivative of y in terms of x is just 1 dy dx equals the derivative of 40, which is 0. Filling this in. We don't know what y is. That's what we're looking for. Now, what are we looking for? The question says how fast. It's asking for how fast the shadow is changing. So it's asking us to find dy dx, or dt, I mean, not dx. These should all be t's right here, not x's. That's a mistake on my part. Which means I made a mistake. Where did I make my mistake? Where did I make my mistake? What's the derivative of x? It's 1, but it has to have a dx dt because x is not the same as t. So we're looking for dy dt. In order to find what dy dt is, we also need to know what x is, which we do. We also need to know what y is, which we don't know. And we need to know what dx is. So we have everything we need except for the variable y. But we can get that using this formula right here. X times y equals 40. X times y equals 40 because we know what x is. It's in our picture. X is 6. $40 divided by 6 is the same as 20 divided by 3, and that's 20 divided by 3 meters. Because it's 40 meters. Don't be find a side of it, so it's a meter. This is 20 over 3 meters. And then now we can fill it in. dx dt can be replaced with 1 meter per second. Y can be replaced with 20 over 3 meters. Plus x, which is 6 meters, times dy dt equals 0. So what we have here is 1 meter times 20 over 3 meters makes 20 over 3 meters squared per second. And then we're solving for dy dt. So we would subtract the 20 thirds over. 6 meters dy dt is equal to 20 over 3 meters squared per second. Where are you at?
In the office. I'm just stealing mine from next period anyways.
You're not supposed to be doing that.
Yes, someone told me I could.
Who told you?
Denise.
Go to the library and check out a laptop. Those are not leaving.
But there's laptops are in this bucket room.
There's another laptop card in the library.
Oh my god, you're stressing me out.
And I don't like to check out the
I'm coming right back with these next period.
I'm just saying. How do we solve for dy dt? Negative 20 over 3? No, y is actually a measurement, not a speed. So the y is actually the side length. dy dt, when we, okay, I see what you're saying. You're saying, should this be a negative right here? Yes, you're right. I was thinking, Miller, I see what you mean. I thought you meant, should our answer for y be negative? You're exactly right. Good morning. And then the last step of the problem is to get the 6 meters over, we do what? We divide. Now, since this is 20/3 over here, instead of dividing by 6, we're going to multiply by 1/6. That way the 6 meters cancel. Meter squared times meter, or meter squared with a meter on the bottom cancel to become meters per second, which is what it should be. We get -20/18 meters per second, which reduces to -10/9 meters per second. It is a negative, and that's what it should be, because as he's getting closer to the building, we discussed yesterday, his shadow would be getting smaller. So that side of the triangle is decreasing. Daisy, you okay with that? It seems like the biggest struggle in physics and with problems like this is dealing with the units, carrying the units along throughout the problem. Okay, going over to the third one. This one's a little tricky. This one requires a little extra work. Requires a little extra work. Because here's what you would run into. You would say, we take the implicit differentiation. We get dv dt is equal to, and we've got to use the product rule. We've got to take the derivative of 1/3 power squared times h plus 1/3 power squared times the derivative in terms of time of h. So we get dv dt is equal to the derivative of 1/3 power squared is 2/3 pi r, because the 2 would get brought down, making the power 1, and the 2 and the 1/3 would turn into 2/3. Dr dt. 2/3 pi r dr dt times h plus 1/3 power squared dh dt. So, let's go through and look at what we have. In order to solve this problem, we're trying to find dh dt. So, I'm going to go and I'm going to circle dh dt. Okay? That's what we're trying to find. In order to find that, we've got to know every single other variable that's listed. We have to know dv dt. Do we know that? Yes. We have to know the height. Yes. We have to know the radius. Is the radius given to us? No. But we could get the radius, because it gives it to us, we could do it as a proportion. This is the radius here. Because remember, we need the radius when the height is 3. Well, what's the radius of the entire funnel? 2. So what we can do is we can set a proportion, a radius to height proportion. So it would be the entire funnel has a radius of 2, and when that happens, it has a height of 6. And we want to know what is the radius when the water level is 3. We could use a proportion to get that answer.
At this time, we're going log down. This is code green. At this time, log down.
Okay, so we can use a proportion to find what the radius is. So now we know what the radius is. We have that piece of information in this problem. So we can check off this and r squared over here. But the dilemma is dr dt. Nowhere in the given information does it tell us the speed of the radius, and with it being a speed and not a constant measurement, not a numerical measurement, it's actually something that's constantly changing, there's no way of knowing dr dt. So what that means is it cannot be done this way. Okay, what's the only measurement that we know the speed of? It's asking, we know how fast it's flowing out, so we know volume, right? And it's asking us to find what? And it's asking us how fast is the water dropping, so how fast is the height changing? So we need to rewrite this formula. We still need to use volume. We need to come up with a formula that has just volume and height in it. Does that make sense? We need to come up with a formula where we have just volume and height written, where R is not taken into consideration. And how we do that is we use this proportion that we wrote a second ago. We're going to use the proportion. Radius is to height. What's the radius of the entire funnel? 2, and the height of the entire funnel is 6, right? We cross multiply, we get 6r is equal to 2h. Now, what variable do we need to eliminate from our formula? R. So we need to substitute something in for r. So that means that we need to figure out what r is. We need to get r by itself. How do we get r by itself here? Divided by 6. So we get r is equal to h over 3. So we have this formula. Volume is equal to 1/3 pi r squared times height. We're still going to use that formula. But we need to get rid of the r because we don't know what the speed of the radius is. So we're going to use the proportion that we have over here. We rewrite r as h over 3. We're going to take that and we're going to plug it in here. And in doing that, instead of having volume being dependent on the radius and the height, the volume will then just be dependent upon the height. So we get volume is equal to 1/3 pi h over 3 squared times h, which gives us volume is equal to 1/3 pi. H over 3 squared is h squared over 9. So our formula for volume is now 1/27th pi h cubed. Because the h squared and h multiplied make h cubed, the 1/3 and the 9th make a 1/27th. Now that does not mean that this formula works for all cylinders, or all cones. It only works for this cone because of the ratio of radius to height. Okay, if this would have been, instead of 2 to 6, if this would have been 2 to 8, that would change this ratio, which therefore would change our volume formula. Okay, so that would have to be recalculated for each problem. But anyways, now we can take the derivative of this. V equals 1/27 pi h cubed. It'd take for derivative with respect to time, so dv dt is equal to 1/27 pi times 3h squared dh dt. And if you look, it's asking us to find dh dt, so this is what we're solving for. In order to solve for this, we've got to know the height, which we do. And in order to solve for this, we also need to know the rate of the volume, which we do. So we have everything in the formula besides dh dt, so now we can finish this problem. The rate of the volume is -2 centimeters cubed per second equals, if you will, this is, I'll just go ahead and go with this, 1/27 pi, 3 times, the height is 3 centimeters to v squared, dh dt. We get -2 centimeters cubed per second is equal to 1/27 pi times 3 times 9 centimeters squared dH dt. This is convenient because what's 3 times 9 make? 27, so we've got a 1/27 and we've got a 27 on the same side. So these just cancel each other out.
Excuse me, please, lockdown is now over.
So we have negative 2 centimeters cubed per second is equal to pi centimeters squared dH dt. And to get dH dt by itself, we divide the pi centimeters squared over. Pi centimeters squared cancels, we get the answer. dH dt is equal to negative 2 over pi. Centimeters cubed divided by centimeters squared turns into just centimeters per second, which is exactly the unit rate that we should have. Because we're talking about the rate in which the height is changing. Since we're draining a cylinder, a cone, it should be a negative number, which it is. And it's in the correct unit rate. Centimeters per second is a measurement of velocity. Rate divided by time. Or distance divided by time. Okay. Another proportion problem. We've got to our formula, 3y equals 2x. Going with that, we're going to take the derivative of both sides with respect to t. So we're going to do the derivative in terms of time of 3y and do the derivative in terms of time of 2x. What's the derivative of 3y? What? 3 dy dt is equal to the derivative of 2x in terms of time. Daisy? 2 dx dt. All right, so looking at this, in order to, what are we trying to solve for? We're trying to solve for how fast the shadow is changing, which is dy dt. The only thing that we need to find this is how fast he's moving towards the building, which we know. So we just plug it in. 3 dy dt is equal to 2 times negative 0.5 meters per second. We get 3 dy dt is equal to negative 1 meter per second. That 3 is a constant. There's no unit attached to it. But so to solve, we still just divide by 3. There's no unit attached to it, so it doesn't change the unit of the other side. Negative 1 meter per second divided by 3 is just negative 1/3 meter per second. There may be one that easy on the test. So that's a straightforward. Once you have the proportion in terms of the calculus behind it, the calculus behind it is really easy. All right, and then the last one in the assignment was number 5. It tells us that a spherical balloon is being drained at a rate of negative 2 centimeters cubed per minute. It wants to know how fast is the surface area changing. So when a ball is shrinking, more air is leaving it. It's going from being a large balloon down to a small balloon. So is the speed of the surface area going to be a positive or a negative? It's going to be a negative because we're decreasing in size. So we should get a negative answer. And surface area. Area is measured in units squared, right? So this is surface area over time. Surface area is measured in units squared. So our final answer should say centimeters squared over time, which in this case is minutes. So our answer should be centimeters squared per minute. Now, it gives us two formulas. Right off the bat, it says, let's find, it's looking for dSA dt, or the speed of the surface area, how fast is it changing. So we're going to take the derivative of the surface area formula. So we're going to take the derivative of both sides. The derivative of S is what? 1 what? 1 ds dt is equal to 4 pi times the derivative of r squared is, actually, 2r dr dt. So, in order to find the rate of change of the surface area, this is what we're looking for. We've got to know the radius, which we do, that was given in the problem. And we've also got to know how fast the radius is changing. Does it anywhere in this problem give us how fast the radius is changing? No. Okay, there's no way to look at this problem and know unless it's given to you, but they do tell you the speed of the volume. And what's the volume dependent upon? It's dependent upon the radius. So if you differentiate this, you're going to have dv dt, you're going to have an r left in it, and you're going to have dr dt. So you're going to know dv dt, you know what r is, the only variable that will be left will be dr dt. So we can use this formula to find the rate of the radius. So coming over here, 4/3 pi r cubed, we differentiate it on both sides. dv dt is equal to 4/3 pi times 3r squared dr dt. I'm going to cancel off the 3's. dv dt is equal to 4 pi r squared dr dt. And if you notice, in order to find the rate of the surface area, we need the radius and we need the speed or the velocity of the radius, how much it's changing. If we differentiate the volume formula, we have a formula that involves radius and the rate of change of the radius. So now we can use this to find the rate of change. dv dt, that's given to us. -2 centimeters cubed per minute equals 4 pi. The radius is 1 centimeter squared dr dt. So what we have is we have -2 centimeters cubed per minute equals 4 pi centimeters squared dr dt. This can be solved by just dividing the 4 pi over. 4 pi centimeters squared over. And we get dr dt. -2 over 4 pi becomes -1 over 2 pi. The centimeters cubed and the centimeters squared reduces down to just centimeters per minute. Which it should, because if you look, it's radius over time. Radius over time. Radius is measured in centimeters, time is measured in minutes. So our units match. Our units match what we're solving for. So we found dr dt. The question's not asking for dr dt. It's asking for the rate of change of the surface area. But in finding that, we need dr dt. So now we're going to fill in this formula. The rate of change of the surface area is 4 pi times 2 times the radius, which is 1 centimeter, times the rate of change of the radius, which is 1 over 2 pi centimeters per minute. And if you're looking at this, you see a pi on top, a pi on the bottom, they cancel. There's also a 2 on top and a 2 on the bottom. Those cancel. So what we're left with is ds dt is equal to -4. 4 times 1 times -1. Centimeters times centimeters is centimeters squared per minute. Our units match what they should. Surface area is measured in units squared, centimeters squared, over time. Time is measured in minutes in this problem. Our units match what the question's asking for. Okay. For your homework for the weekend. Number 6. Guys, 6 is a cone problem. 6 is a cone problem. So it's going to be done very similar, almost identical to the previous cone problem. It's got different numbers involved, but the concept's the same. Also do number 8. Number 8 is a Pythagorean theorem problem. Okay, it's going to be a right triangle. And then number 21A. Number 21A, and this is a proportion problem. And that'll be it. Okay? Very similar to the problems that we've already done. It's worded a little different, but inevitably it's the same problem. So do those 3 problems for the weekend. Let's take them up for a grade at the beginning of class. Okay, let's take those up for this will be our first grade in the 9 weeks.